Hi everybody. In this series of videos, this being the first of them, I want to pose a fairly high-level mathematical challenge. And the challenge comes in three parts, and I'm aiming this video at three different audiences. The challenge is to eliminate the notion of infinity from mathematics. That is, to get rid of infinity. Don't allow it in. And the three parts are of the challenge. First, if you don't think that's a good idea, then I challenge you to tell me why not. And the second part is, if you do, second and third parts, if you do agree with me that we should get rid of it, then the challenge is to help me figure out how to proceed. And for that, it takes specialized mathematicians, as I see it, in two areas. One is in the foundations of mathematics, and that is to figure out an axiomatic system that we can build mathematics upon that does not admit infinity. And the third part of the challenge is also for mathematical specialists, and those are the experts or specialists in the calculus and analysis, and that is to prove the theorems of calculus without requiring the notion of infinity. That'll require new definitions of limits and continuity and convergence and so on. So the three challenges don't necessarily line up with the three groups of people, depending on what you believe. But in this video, to open it up, I'd like to make the case that it's a bad idea to allow infinity into mathematics, and that it would be a good idea to get it out. Now, infinity has had a long history. It was talked about by philosophers and theologians for thousands of years, and mathematicians even talked about it, although it confounded them. Way back in ancient Greece, Zeno saw that it led to paradoxes. It logically implied that you couldn't shoot an arrow to a target. It would never get there, so on. So the notion was fuzzy, ill-defined, and led to problems, as I see it, all through those thousands of years, both in theology and in mathematics. And in physics, it always presents a problem if it ever shows up, even though most physicists don't believe there's anything infinite in nature, and so we don't need it to describe nature. It's just a problem when it shows up. In fact, the Nobel Committee gave Richard Feynman a Nobel Prize for figuring out a clever way to get those infinities out of some mathematical equations used in physics. So I think it's been a cloudy, dubious idea for thousands of years. But then around 1900, around the turn of the 20th century, Georg Cantor first dealt with the notion of infinity in a rigorous way and put the notion on a sound mathematical basis. And then he developed his theory of infinity. I don't know if it goes by that name, but it's well known to anybody who studies mathematics. And he proved that there are some really confounding, non-intuitive consequences to accepting infinity. That is, that there are more than one size of infinity or level of infinity. In fact, there are an infinite number of sizes of infinity. One of the conclusions that Cantor came to. Now, another conclusion he came to immediately was what he dubbed Cantor's paradox. And this is a paradox similar to Russell's paradox, having to do with the set of all sets. I won't go into the paradox right now, but immediately he saw the problem, and so mathematicians began looking for ways to get around the problem. And as I see it, they swept it under the rug by just agreeing to not talk about things that scare up that particular paradox or those paradoxes. but I think it got worse. Now, immediately there was a controversy. When Cantor talked about infinity, this rigorous notion of it, he was opposed by Leopold Kronecker and Brouwer in the Netherlands and others who took the position that I take, sort of, that we shouldn't allow infinity into mathematics because it brings nonsense with it, brings paradoxes with it. But supporting Cantor was, among others, David Hilbert, who was probably the most powerful mathematician at the time. And Hilbert thought that this was one of the most wonderful contributions to mathematics ever made. And as a result, that faction won the day, and mathematicians for the 100 years following, now 113 or so, have adopted Cantor's notion of infinity and accepted it into the body of mathematics, right along with all of those prohibitions that you have to observe in order not to run into the paradoxes. I side with Kronecker, although not exactly, in that since infinity brings along with it paradoxes, which are the same as a euphemism for inconsistency, and inconsistency just should not be allowed in mathematics. We should not allow that notion into mathematics because it makes mathematics inconsistent. Seems simple enough to me. And in fact, the way I see Gödel's theorem, which rocked the world of mathematics in 1927 or thereabouts, he proved that you can't have any consistent and complete system of mathematics if it is robust enough to contain the integers. And to me, it's the robustness that admits integers that is the problem, because when you admit integers, you're admitting infinity. Because even to this day, most all mathematicians will agree that there are an infinite number of integers, and they have for thousands of years. And that's what I would like to challenge and eliminate. I would like to eliminate that notion that there are an infinite number of integers. And that's where I depart from Kronecker. Kronecker is famous for saying, God gave us the integers, all the rest are the work of man. And the implication is that God gave us the infinite set of integers. He didn't just give us a finite set. Well, my proposal is that we limit the integers to a finite set. And that is, we admit that there is a largest integer, and then build our mathematics around that. And so, of course, the naive objection to that is immediate, that, wait a minute, if you have a largest integer, say m, I can add 1 to it and get m plus 1. So there. And I'd point out that if we've defined our set of integers to be those from minus m to plus m, for example, then we have to define what we mean by addition for each pair of integers from minus m to plus m, and we simply don't define the sum m plus 1. And so your trick of trying to add 1 to m doesn't work, because there's no such thing as addition between m and 1. Now, I'm not saying that there is a largest integer. And if m is too small, it cramps what you want to do, or limits you from what you want to do, you're perfectly at liberty to choose a larger m. You can choose one that's much bigger if you want, and then make a mathematical system around that. And then, of course, you do have the sum 1 plus my old m. That would now be in your bigger system. So you can always make a bigger system. But in any system that you do any computation in, there always will be a largest integer in that system. Think about calculating systems. Think about using an abacus, for example, to add and multiply. Well, the abacus has a finite number of wires with beads on it. And whatever that number is, if there's 25 wires, then you can only hold numbers up to 10 to the 25th minus 1. And you try to add 1 to that number and you run off the end of the abacus. You don't have another bead or another wire to push. And so you're limited by the construction of that abacus, which is equivalent to the definition of the numbers available in your system. And the same is true with pocket calculators. You have a certain number of digits in the display, and if those all contain 9s, and you try to add 1 to that number, you will somehow mess up your calculator, or you'll get nonsense, or you won't get the correct sum, because the display can't hold a number that would represent the correct sum. And so is it a limitation? Well, it sure is for any application of that calculator. But there's nothing to prevent someone from building a calculator that has 50 display digits. And if that's not enough, build one that has 500 display digits. So there is no absolute limit to how big numbers can be, but in any practical application there is. And so all of our computers, whether the size of the number it can deal with is determined by the word size in the computer or by the software used to calculate sums and products and so on. Whatever the limitation is, there is a limitation, and computers cannot handle infinitely large numbers. So I propose that we develop a mathematical system with one of the axioms that, or however we state it, that there is a largest integer, say m, and these will define what I call practical numbers, and that is a set of numbers smaller than m that we can add and multiply and do arithmetic with impunity without generating numbers that are bigger than m. So m is the largest defined integer, but something smaller than that would be the largest practical number. And this is exactly like we have in our computers. Practical numbers would be those that you can do the arithmetic on without overflow or underflow conditions. Or you can do the calculations on your abacus and have enough beads to do the job. Now, that's the challenge. That's the case that that I made to that it's a bad idea to allow infinity into our mathematical system. And so the challenge is to either tell me why I'm wrong, or to agree that I'm right, and then either if you're a high-powered mathematician that's able to work on the foundations and figure out how we can develop an axiomatic system that will support practical numbers, then I'd ask you to take on that challenge. Or if you're high-powered enough to take on reproving the fundamental theorems of calculus so that we can still do the same computations, because I believe that the results of computation in practical numbers will be identical to those in continuous mathematics, those that the mathematics that admits infinity, because in reality all calculations done using current mathematics, even though it's believed to be continuous and based on infinity and infinitesimals, all computations using that mathematics are using practical numbers anyway. They're always all computations use only finite numbers, or finite numbers less than some maximum. So my challenge is, if you're expert, work on foundations, work on a new proof of the calculus, or if you're a young student, maybe the next Einstein, maybe the next David Hilbert, My challenge to you is to tuck this away in your brain, and as you learn the mathematics through your career and as you succeed in getting your degrees, be ready to pull this out and challenge the orthodox mathematics that you'll be learning, and maybe you can make a contribution. It's my belief that if we had a grainy mathematics, which is what this mathematics would be, it would be much more suitable to describing our universe, because scientists are determining that our universe is grainy at the root after all. We live in a grainy world. Why not use a grainy mathematics to describe it? And it's only fair to take on this challenge because Cantor's had over 100 years now to play with his idea and to develop mathematics based on infinity. And we don't need to throw that away. That's valuable for whoever wants to play around with infinity. But what we need is a new mathematics in addition that's different, but yet has the same computational results and capabilities, but I think will go further toward describing our real world. So the next couple of videos will describe in a little more detail my approach to how I think mathematics should be improved. So take on my challenge, check it out, and check out the next videos, and please leave me comments. Thank you for watching.